Alright, we're going to start this section by talking about objects that at first astronomers thought were unique and different objects. It turned out to be parts of objects we already knew about. Those objects would be what we call quasars. Quasars were first discovered in the 1960s by radio astronomers. They were radio sources that were seen in the sky with radio telescopes, and they corresponded to objects. When optical astronomers turned their telescopes toward the position of these radio sources, they found nothing very substantial there. They found basically what looked like faint blue stars. And because they looked like faint blue stars, they called these objects quasi-stellar objects, meaning they were sort of like, they looked like stars, but they weren't stars. So stellar meaning like stars, quasi meaning sort of like stars. QSOs for short, or quasars as an abbreviation. And you can see this one here looks just like a normal star. If that little orange arrow weren't pointing to it, it wouldn't look any different than the stars you see around it. But what astronomers found is that when they took the spectrum of these stars, they looked very, very different indeed. Instead of having a sort of a peak and valley spectrum, or a blackbody spectrum, a typical stellar spectrum that has a peak wavelength and then diminishes as the wavelengths get longer, it had a continuous spectrum that was kind of a weird sloping spectrum like that. Also, instead of having absorption lines like stars do, an absorption line on this, for example, would have divots in the spectrum, whereas here you have little sort of peaked, sort of inverted spikes coming up. These are what emission lines look like on a intensity diagram. And these emission lines were at really weird positions in the optical spectrum. They didn't correspond to any known spectral lines that were seen in emission before. So some astronomers jumped to the conclusion that perhaps we're looking at a totally different and new element that has totally different emission lines. But in fact, they just were not used to seeing emission lines like this that were so incredibly highly redshifted. In fact, with this line here, this very tall spike, is actually the red line of the hydrogen-Balmer series. So this is the red line of the hydrogen-Balmer series, but it's shifted way over into the invisible to our eyes, infrared. This is the bluish-green line of hydrogen, the H-beta line of the Balmer series. This is shifted from blue-green into the yellow. And the two violet lines of the Balmer series, the H-gamma and the H-delta, are shifted into the green and light blue part of the spectrum. And so what this means is that the quasars not only had these unusual spectral properties of emission lines and a non-thermal spectrum, a non-blackbody spectrum, but they also had huge redshifts. Okay, so they had weird non-stellar spectra, and they had huge redshifts, meaning these objects were moving away from us at very, very high velocities, which was very curious, very peculiar, not something you would expect. Certainly not something you would expect if these objects were within our galaxy, because they were all moving away from us, and they were all moving away at a good fraction of the speed of light. They also, however, had rapid variability, and we'll talk about why that's important in a few minutes. But in other words, they would sort of flicker in an irregular way in fairly short time periods, within a few days or a few weeks. So we'll get back to that in a few moments. The thing is, if the redshifts conform to the Hubble law, remember the Hubble law said that the velocity, or the distance basically, the distance of the object was equal to the velocity that it's receding from us divided by the Hubble constant. If you just flip around the Hubble law and solve for distance, we know the distance is basically proportional to how fast the object's moving away from us. The faster galaxies are redshifted away from us, the farther away they are. If these redshifts were the same kind of redshifts that were causing the galaxies to fly away from us, then it implied enormous distances beyond the farthest visible galaxy, at least the farthest visible galaxy that was visible back in the 1960s. So if these things were cosmologically redshifted, caused by the same phenomena that made the redshifts of the galaxies, it meant that they were extremely far away. And if we were able to see these objects, even if they were fairly faint, like this little guy here, and they were at these enormous distances, it means they had to be extremely luminous. They had to be extremely bright, 10 to 1,000 times brighter than a typical large galaxy. So all of this became quite an extraordinary thing. Now let's go back to this rapid variability in brightness issue, because now we know that that turns out to be very important. If this were an object within our galaxy that was star-like, it wouldn't be very exceptional to have rapid variability in brightness. However, because it's so enormously far away, and because it's so enormously luminous, it means that it must be insanely bright, and the only objects we know that are anywhere near that bright are very large objects like a galaxy full of stars. But to have rapid variability means that this object must be relatively small. Not as small as a star, but certainly as small as, say, a solar system. Let me see if I can explain this. Rapid fluctuations of brightness imply small size. Basically, an object like a galaxy cannot flicker on and off rapidly. This is a picture of the Andromeda Galaxy, and we're seeing it at an oblique angle. So, for example, let's say the distance between this near side of the galaxy to the far side of the galaxy is about 100,000 light years. Okay? That means if I could somehow flick a magic switch to turn off all the stars in the Andromeda Galaxy simultaneously, so that the whole thing went dark simultaneously. First of all, that would be impossible. Let's just say I can. If all the stars magically burned out at the same exact time, what would you see? Well, first of all, you wouldn't see anything if it happened tonight, because it would take over 2 million years for that light that was created to travel to you, or the lack of light to travel to you, basically. And so what you would see is about 2 million years from now, you would see this edge of the Andromeda Galaxy go dark first, then a little farther in, and a little farther in, and a little farther in, and then the core, and a little farther beyond that, and a little farther beyond that, and finally the other edge would go dim and disappear. But the whole process would take 100,000 years, because the thing is 100,000 light years across. Okay? So an object can't change its brightness in less than the light travel time to cross the object. It's just not possible. Now, even if you only did the small inner portion here that might be maybe not 100,000 light years across, but certainly several thousand light years across, somewhere around 10 to 20,000 light years across, it would still take thousands of years for it to vary in brightness significantly. Okay? So if we have a quasar that fluctuates significantly in 5 days, it can't be larger than 5 light days across. It can be smaller, okay, but that puts a limit on the size. It can't be any larger than the light travel time it takes for the variation, equal to the variation in light. So this limits the size of most quasars to a few light weeks across or less, and some smaller than a few light days. Well, now we're getting to about the size of our solar system. Our solar system is maybe a couple of maybe a light day across, and maybe a little bit larger, depending on what you consider part of the solar system. But we're talking roughly on that order of size. Okay. Now, here's the other thing. So we know that it's fairly small, and it's also extremely bright. So you have all that brightness coming from a very, very small region of space. A huge luminosity implies a huge mass. Okay? It turns out when you have an enormous amount of light being produced in a small region of space, that light produces radiation pressure. And that radiation pressure, if it's being applied to a single object or a single structure, can blow that structure apart unless there's a strong enough gravity to hold the material in. So there's a maximum luminosity an object of a given mass can have before it blows itself apart by radiation pressure. So in other words, the more luminous the object, the more mass it needs to hold itself together. And so if we know the luminosity, we know that there's a minimum mass it has to have for it to not be totally blown apart. And it turns out for the kind of luminosities we have for quasars, you need millions and millions of times the mass of the sun to hold the structure that's giving off the light together. So what can a quasar be? Okay. Well, quasars have huge luminosities. Luminosities are around 10 to the 39th watts. And if you do the math, that implies a mass of at least 10 to the 8th solar masses, 100 million solar masses. And yet some, the emitting regions of some, we know from their variation in light, is less than a light day across. So what in the world, what in the universe can be so massive and so small? Well, you have probably guessed it, if you haven't, of course, read it in the book already. It's the radius of a black hole, a 10 to the 8th solar mass black hole is, well, if you remember, we said it's 3 kilometers for every solar mass worth of matter. So that turns out to be 3 times 10 to the 8th kilometers. 3 times 10 to the 8th kilometers is approximately, well, that's 300,000 kilometers, or rather, I'm sorry, 300 million kilometers. Well, the Earth is 150 million kilometers from the Sun. So we're talking about the diameter of the Earth's orbit. So the radius of a 10 to the 8th solar mass black hole is approximately the diameter of the Earth's orbit. And of course, the radiation wouldn't be coming from the black hole. It would be coming from a disk of material falling into that black hole that's outside of that supermassive black hole. Now, we know that supermassive black holes exist. We showed that already. But now we know that they must be the engines for these quasars. So matter falling into a black hole accelerates to nearly the speed of light, and that's why they tend to give off lots and lots of energy, including X-rays, things like that. So it's a great way to get a lot of energy from a little bit of mass because of the acceleration of these gases as they fall into the black hole. So it was theorized or hypothesized for a long time that perhaps these quasars are supermassive black holes that have matter falling into them. How much matter would you need to fall into a supermassive black hole to produce 10 to the 39th watts and sustain that sort of output? Well, it turns out about 1 sun per year. Most quasars would need to be fed about a solar mass per year to account for their luminosity. That's a lot, but it's not ridiculous. As you know, of course, galaxies have hundreds of billions of stars, so losing a solar mass per year doesn't amount to very much. So quasars, we think, are basically supermassive black holes in the centers of distant galaxies, because some of the early quasar photos showed fuzzy wisps surrounding the bright source, and that was the best our telescopes could do back in those days. But then it became clear that these quasars were actually the ultra-active cores of distant galaxies. It was just hard to see that there were galaxies there because the quasars in the center were so bright. And since they are billions of light years away, and we don't have any quasars in the closer universe, it means we're looking far back in time. So quasars were relics of the early universe, and it may be that quasars are an evolutionary stage in normal galaxy formation. And that's what we're going to continue with in the next part.